In this video, we are going to discuss powertrain modeling. Specifically, we will talk about how to actuate vehicle models with power sources, build driveline mechanisms, create multi-speed transmissions, and modeling engines. This training will be applicable for both the combustion engine and electric teams since it talks about modeling transmissions in general. Modeling engines section will be specifically useful for combustion teams. For electric teams, refer to Simscape fundamentals and vehicle drive and control videos for more information on modeling DC motors. We would also like to acknowledge and thank the Virginia Tech Formula student team for providing us with data about their vehicle, motors, engines, and batteries for us to use in this training. So far, we have created a working vehicle model with brakes and tires. However, the motion has been entirely due to gravity as it descends on a slope. The next step is to add a drive mechanism. This will allow us to model the vehicle to move under its own power. We will start with a direct drive model, that is, no transmission, and progress towards a higher fidelity model by adding more detailed components, that is, clutches and gears. By the end of the chapter, we will have a working 3-speed vehicle model. First, we will use ideal power sources to analyze the effects of changing the transmission gear ratio and the vehicle speed. Finally, we will replace the ideal sources with an engine source. Let's switch to MATLAB to start with the direct drive model here. Let's open a starter model vehicle_direct drive_start. This is the vehicle model we developed in the Introduction to Vehicle Modeling video. Let's access the contents of this subsystem. We have our brakes, sensors, and a vehicle subsystem. Inside the vehicle subsystem, we have our vehicle body, tires, and wheel quantity measurements that we implemented in the vehicle modeling video. At the top level, we can see that the wind is set to 0, and the terrain is also set to 0. This means there is no headwind and the road is flat for our model here. The brakes are enabled at 50 and 75 seconds respectively after the start of the simulation. This vehicle model will not move until we actuate the rear axle since we are on a flat terrain. There are two types of rotational mechanical inputs you can use to actuate vehicle models: angular velocity and torque. To create the direct drive mechanism, let's first use an angular velocity source. To do this, go ahead and access your Simulink library browser here. Scroll down to Simscape. Under Foundation Library and Mechanical, go to Mechanical Sources to find your ideal angular velocity source here. Drag one of these blocks into your model. I'm going to rotate this block using our shortcut Ctrl R. Block and a Simulink to physical signal converter block to convert the Simulink signal to a physical signal. To do this, let's go ahead and access our Simulink library browser, scroll up to Simulink, and then Sources to find our constant block here. Next, we need a converter block. To do this, access the library browser again, scroll down to Simscape, and then Utilities to find our Simulink to physical signal converter, and drag one of these blocks into your model. Let's connect the constant block to the converter and the converter to the S port of the ideal angular velocity source, which is expecting the physical signal to be converted into the angular velocity value. Let's set an angular velocity value of 500 RPM. To do this, double-click on the constant block and set its value to 500 and select OK to save changes. To set the units for the signal, double-click on the Simulink to physical signal converter block and change the units from 1, which is the default value. Recall that the default unit for angular velocity is going to be radians per second. So let's change this to RPM and then select OK to save changes. Because the vehicle will be driven by the rear wheel, connect the R port of the ideal angular velocity source to the same physical connection as the rear brakes, in this case, the rear axle here. We can double-click on this block to see that the rear axle is directly connected to the same physical connection as the rear brakes here. Let's go back one level up. This angular velocity value here is going to be provided with respect to a reference, so our C port here becomes the reference node. Let's go ahead and connect a mechanical rotational reference block here. To do this, go to the Simulink library browser and scroll up to mechanical and then rotational elements to find the mechanical rotational reference here and drag one of these blocks into your model. And let's go ahead and connect this block to the C port of the ideal angular velocity source. The interesting thing to analyze from this model is to view the torque required to maintain the input angular velocity that we have prescribed here. To measure this quantity, let's connect an ideal torque sensor block directly in series with the rear axle. To do this, let's go ahead and access the Simulink library browser again. Go to Mechanical Sensors and drag in an ideal torque sensor block. Let's delete the connection between our power source and the rear axle and connect our ideal torque sensor directly in series with the rear axle here. So let's go ahead and connect the ideal angular velocity source to the other side of the torque sensor. The torque sensor's output is a physical signal, so in order to convert that to a Simulink signal to be connected to a scope, we need a converter block. To do this, go to the library browser again, scroll down to Utilities, and drag a physical signal to Simulink converter block. Connect this to the physical signal here. Let's drag in a scope block next. To do that, go up to Simulink, Sinks, and then find the scope block here and connect the output of the converter block to the scope block. This is going to be our torque measurement. Let's go ahead and simulate the model now. Take a look at the vehicle speed here. Because the vehicle is being directly driven by the angular velocity source, it impacts the rear wheel axle. The vehicle speed is therefore proportional to the input angular velocity signal. In this case, since the input angular velocity signal is constant, the output vehicle speed is also constant. We also see a large acceleration during the start. We can analyze the acceleration here in the velocity signal better with the wheel quantity measurements. To look at this, let's go inside the subsystem here and the vehicle subsystem to look at the wheel quantities measurement here. Here we have the rear and the front wheel slip values and the rear and front normal force values. We see that there's a huge slip in the rear wheel at the start. This is because we are forcing the tires to reach the prescribed angular velocity from zero in an almost instantaneous fashion. We can also see the effect of acceleration here on the front and rear wheel normal forces. Load shifts back for acceleration, so it is higher for the rear wheel. The next interesting thing would be to observe the torque required to maintain the constant angular velocity condition that we have here. To do this, let's go back to our model here and access the top level and open up the torque scope here. Let's also bring in our speed scope here. As the vehicle accelerates to a speed of 40 km per hour, we can also see that the torque increases during this acceleration. Once the vehicle stops accelerating, a steady state torque is maintained. Note that in this model, we are applying brakes and power to the axles at the same time. This is because we don't have any control logic to monitor this scenario. Although this is not realistic, we can see that despite the fact that the brakes are applied at 50 and 75 seconds, the ideal angular velocity source keeps providing whatever torque is required to maintain the prescribed speed. This is why the vehicle does not slow down even though the brakes are engaged as shown in the speed plot here. This shows to some measure the effect of disturbances on ideal angular velocity source that we have here. Let's go back to our model here. Note that the initial speed set by the source here is 500 RPM. However, let's go ahead and access the tire block here. And if we go to the Dynamics tab, we see that the initial velocity specified for the tire is 0. Let's go back to MATLAB here. This is the reason why we are seeing the initialization warning here on the MATLAB command prompt. Be aware that using velocity sources requires us to specify stricter initial conditions. In this case, we could fix this warning by providing 500 RPM as the initial speed for the tires as well. Next, instead of the ideal angular velocity as a source, we could also provide an ideal torque source for actuation. Whereas the angular velocity source can be used to compute the torque required to reach a particular speed, the torque source approach can be used to test how fast you could go given some torque restrictions. Let's pull up an existing model for this. Let's open up vehicle_direct_drive_torque here. This model is the same as the model that we just built, except for the fact that we have an ideal torque source instead of an ideal angular velocity source here. Let's go ahead and simulate this model here and take a look at our speed scope here. We see that the acceleration is not that high in case of the torque-driven system here, since we have restrictions on the amount of torque that is available. We can also see this in the wheel quantities. To see this, let's go ahead and access the subsystem here, and inside vehicle subsystem, open up the wheel quantity scope here. We see that the initial slip now is not that high anymore. We can also see the effect of brakes applied on wheel slip and normal force values at 50 and 75 seconds here. Let's go ahead and take a look at our speed scope again. Because of our torque restrictions, we also see that brakes slow down the vehicle in this case, whereas in our first approach, this resulted in only increasing the available torque to maintain that speed. Let's go back to the presentation to do a small recap. We applied power to the rear axle where the rear brakes are also applied. We then used a constant angular velocity source and measured the torque required to maintain that speed. After we simulated the model, we saw the constant acceleration and the steady-state speed of the vehicle. We looked at the wheel quantities to see the instant acceleration demanded by the system, which caused a large slip on the rear wheel and also shifted the load to the rear. We then saw the torque values peak to achieve the acceleration and the steady-state torque after it. Finally, we saw the effect of brakes on the ideal angular velocity source. The vehicle did not slow down because the source provides all the torque that is necessary to maintain that speed. Next, we used an ideal torque source instead and measured the speed values under limited torque conditions. After we simulated the model, we saw a smoother acceleration resulting in a smaller wheel slip. We also saw that since the system had only limited torque, that is, the constant torque provided by our ideal source, brakes now had an effect on the vehicle speed and tire normal forces. We have been working with the direct drive models here, where the power input is directly connected to the axle. In reality, there is a transmission system between these two components. This includes components like clutches and gears. Next, we will build a 3-speed transmission system. As a first step, we will build a single-speed system to understand how clutches work and increment to a 3-speed system. Let's switch to MATLAB to see how to do this. Let's first open up a starter model here. In this case, it's going to be called gear_start. Here, we have an ideal angular velocity source as a test source for our gear subsystem. We will build our transmission model inside the gear subsystem. This subsystem receives gear inputs as a custom signal through the signal builder block here. Let's double-click this block and take a look at the signal here. Initially, it's in the second gear here, then switches to the first at 4 seconds. Signal builder block can be used to interactively create custom signals like this. Let's go back to the model here. The gear subsystem is also attached to a load, in this case modeled by an inertia and a damper. We are measuring the input and output speed of the gear subsystem using the ideal rotational motion sensors here. Let's now go inside the gear subsystem here. It contains an inertia block to model the inertia of the transmission mechanism. Port A is where the angular velocity source, that is the power input, is connected. Port H is connected to the load. When they are directly connected like this, it models a gear ratio of 1:1. However, there are no mechanisms here to couple or decouple the power input. These mechanisms would be needed to model multiple gears. In automotive systems, this is achieved using clutches, which push multiple flat plates so that friction decouples or couples the power input. These types of models are available in Sim Driveline. To take a look at this, let's go to the Simulink library browser here, scroll down to Simscape, and then Sim Driveline, and under clutches, we can see different types of clutches here. In this library, the block that closely resembles our mechanism is the disc friction clutch block. Let's go ahead and add this to our model. This clutch engages when the applied plate pressure at port P exceeds an engagement threshold pressure. Once engaged, the plates experience frictional torques that enable them to transmit power between the base drive shaft, that is port B, and the follower drive shaft, that is port F. To connect this block to our system, let's go ahead and delete this direct connection here. Connect the B port to the power input here, and the F port to the load here. Let's explore the block parameters now. To do this, double-click on the block. The Geometry tab here lets us set values for the number of friction surfaces, size, etc. Changing these parameters affects how much friction is required to couple the driving and driven shafts. For example, the larger the number of friction surfaces, the better the coupling is. Similar to the brake blocks we used in the vehicle modeling video, we can also set friction and viscous drag torque coefficients in this block as well. Note that the engagement threshold pressure is a parameter here, and the input pressure signal should be greater than this value for the clutch to engage. Finally, the initial conditions of the clutch can be set here. It can be set to locked or unlocked based on whether you want it to start engaged or disengaged. For our application, the default parameters of this block work for us. So let's select OK to save changes. Next, we need an actuator for the clutch that can provide the engage-disengage pressure signal based on the gear input. We can build one using Simulink and Simscape blocks. Let's open a pre-built block for this. To do this, I'm going to go back to MATLAB and open up actuator_subsystem here. This block outputs a pressure signal based on the input gear command. Let's go ahead and access the subsystem here. We can see that this actuator will send a non-zero pressure signal when the gear command is true and 0 otherwise. Let's go back to the top level of the model here and copy the subsystem and use it in our gear subsystem block here. So for our model, when the input gear equals 2, it would send a non-zero pressure signal, otherwise it outputs 0. Connect the engage port to the pressure signal port of the clutch here. Note that we are using an equality operator here, and this outputs a 0 or 1 based on whether the input signal passes the equality condition. This block can be found by going to the Simulink library browser, scroll up to Simulink, and then logic and bit operations to find the compare to constant block here. Let's go back to our model. Now let's go ahead and simulate the model and take a look at the speed at the input and output of the gear subsystem. While the clutch is engaged between 1 and 4 seconds, the transmission mechanism rotates at the rate of 1 radians per second. This is equal to the input speed. After disengaging the clutch at 4 seconds, the system slows down due to damping. Note that the actuator described here is a simple pressure signal, but we could also add an entire multi-domain mechanism in the form of a Simscape network if we needed that much complexity in the model. You can explore this concept in the pneumatic clutch actuator exercise for this video. Let's go back to the model here. This is still a single speed system. Now let's add low and high gears to this system to make it a 3-speed system. To do this, let's open up a starter model. I'm going to go back to MATLAB and open up gear underscore 3 speed underscore start. This model is same as the starter model we used for the last example, except for the contents of the gear subsystem. Let's go ahead and access the subsystem here. We just built the connection for the middle gear in the last example with a 1:1 gear ratio. Let's go ahead and add 2 more gears, a low gear with a gear ratio of 2:3 and a high gear with a gear ratio of 3:2. We have already set up actuators for the low and high gears here. Notice that we are using go to and from blocks for the actuator connections. The go to block passes its input to its corresponding from blocks. These blocks allow you to pass a signal from one block to another without actually connecting them. The blocks are matched by the use of go to tags. To implement the 3-speed system, let's start by copying the clutch block for the low gear and the high gear here. I'm going to rename this to low and high. Connect the base port of the clutch block to the power input, in this case the A port here. Go ahead and connect the engage port of the actuators to the pressure signal for the clutch block. Now the output of the clutches need to be fed to some form of a gear ratio. Sim driveline provides several gear blocks. To see this, go to the Simulink library browser, scroll down to Simscape, and then Sim driveline and access the gears library here. For our model, let's choose a basic block and drag in the simple gear block into our model here. This block represents a gearbox that constrains the 2 connected drive shafts, the base B and the follower F, to rotate with the specified gear ratio. So let's rename this block to be the low gear and go ahead and specify the gear ratio for this block by double-clicking on this block. Note that here we specify the teeth ratio instead of the gear ratio. So for a gear ratio of 2:3, the teeth ratio is going to be 1.5. Note that this block models gears in a more detailed way compared to the gearbox block from the foundation library that we used in the Simscape fundamentals video. First, we can choose whether the driven shaft rotates in the same or opposite direction to that of the driving shaft. For our model, our output shaft is going to be in the same direction as that of the input shaft. Apart from this, we can also include meshing losses and viscous losses in these tabs here. This block also models the effects of heat flow and temperature change through an optional thermal port. To expose the thermal port, let's go back to the model here, right-click on the block, go to Simscape, Block Choices, and say Show Thermal Port. The H port that just appeared is the thermal port. For our model, we'll stick to no losses and not model thermal effects, so let's go ahead and cancel this thermal port by going to the Simscape Block Choices and saying No Thermal Port. Double-click on the block, make sure that the teeth ratio is set to 1.5 and the output shaft rotates in the same direction as the input shaft, and select OK to save changes. Now let's make a copy of this block for the high gear. Let's rename this block to be high gear. Double click on this block to set the gear ratio. Note again that this is the teeth ratio. For a gear ratio of 3 to 2, the teeth ratio is going to be 0.67. Select OK to save changes. Now let's go ahead and make the connection between the clutch and the gear here. Similarly, the clutch and the high gear here. The follower drive shafts are going to be connected to the load here. Let's go back to the top level of the model here. Note that gear shift is provided by the signal builder again. We see that there is an upshift after every 10 seconds. Low, middle, then high. Let's go ahead and simulate our model to see our output speeds here. And take a look at our scope here. Here we see that the output speed changes after every 10 seconds. First 10 seconds, the speed is lower than the input because of the low gear ratio of 2 to 3. Next 10 seconds, the speed is equal to the input because of the middle gear ratio of 1 to 1. And then for the last 10 seconds, for the high gear, the gear ratio is 3 to 2, so the output is greater than the input. Let's go back to the model here. Apart from using the gears library to build custom transmissions like this, you could use blocks from the transmissions library in Sim Driveline. To look at this, go to the Simulink library browser, and under Sim Driveline, go to Transmissions. This can be used to build various popular multi-speed transmissions. Let's go back to our model here. The final step now is to integrate the 3-speed transmission into the existing vehicle model. Let's go ahead and copy the gear input and the gear subsystem here using Ctrl+C, our shortcut. Let's go to our direct drive model here. Go back to the top level. Recall that we are using an ideal torque source here to provide the power input to the system. Let's delete the connection between the source and the torque sensor here. This provides the power input to the rear axle. And let's put in our gear subsystem in between these two systems here. So let's paste using our shortcut Ctrl+V and connect the output of the gear subsystem to the input of the torque sensor. Notice that here is where our rear axle connection is, and connect our power input to the input of the gear subsystem here. Let's go ahead and simulate the model and take a look at our speeds here. We see the gear changes here at 10 and 20 seconds. Higher gears result in lower torques, hence lower acceleration. We also see that the brakes slow down the vehicle at 50 and 75 seconds. Let's take a look at the vehicle wheel quantities here again. To do this, let's go inside the subsystem and the vehicle subsystem to access the wheel quantities and take a look at the slip and the normal forces. We see the effect of brakes and gear changes here as well. Let's go back to the top level of the model here and take a look at our torque plot. We can see that the output torque of the transmission decreases with higher gears. This is because of the way in which we have set up our gear ratios. Let's go back to the presentation to do a recap. We talked about the disc friction clutch block and how it can be used to engage and disengage gear systems. This block needs a physical signal to actuate it. We then discussed the actuator. This system converts the shift signal to a clutch plate pressure. Pressure applied should be greater than the threshold pressure of the clutch plate to engage. We saw how the speed was maintained when the system was engaged and how the speed decreased because of damping effects after the clutch disengaged. After that, we built the 3-speed transmission system. We used simple gear blocks with 2 different gear ratios to create high and low gears. We also briefly explored other gears on offer with the Sim Driveline library, and also a built-in library for multi-speed transmission systems. We tested the vehicle to look at the effect of the gear system on the speed under a constant torque source. We saw that the vehicle accelerated and went through the gear changes. We also saw that the brakes slowed down the vehicle. We looked at the wheel quantities and the torque plot to see the decreased amount of torque for higher gears. All this while, we have been using ideal sources. The ideal torque source is good for initial iterations of the model. However, it is not realistic because it assumes the source is powerful enough to maintain the specified torque regardless of the angular velocity across the system. In reality, torque and engine speed are dependent on each other. The next step is to add an engine model to do this. Let's switch to MATLAB here. In our direct drive model here, let's replace this ideal torque source by an engine source. Sim driveline provides an engine block. To see this, go ahead and access the library browser here, and under Sim driveline, go to Engines to find the generic engine block. Drag one of these blocks into your model. The engine block has several ports. A throttle physical signal input specifies the normalized engine torque. This is a value between 0 and 1. Let's go ahead and delete the torque source here. And we will reuse this constant for our throttle. So I'm going to rename this block throttle constant. Since this value needs to be between 0 and 1, let's double-click this block and set it to some value, for example, 0.1, which is 10% throttle. Let's also change the Simulink to physical signal converter units from Newton meter to 1, because our throttle has no units. So select OK to save changes. Let's go ahead and make some way for our engine block here. Go ahead and connect the output of the converter block to our throttle input here. Based on this throttle input, the block reports the power and fuel consumption rate through the ports P and FC respectively. B and F are rotational ports that specify the base and follower shafts. So let's go ahead and connect the rotational reference here to the base port here, and the follower shaft to the main drive shaft here. We are not going to be using the power and fuel consumption ports for our model here. The next step is to parameterize the engine block. To do this, double-click on the engine block. There are several ways to parameterize the engine block as shown here. We can use polynomials or provide torque speed data or power speed data. Let's use the tabulated torque data. Here, we specify speed and torque vectors as parameters. We can use MATLAB variables for this. So let's load this data first in MATLAB. To do this, I'm going to switch back to MATLAB here and double-click on the engine data file to load our data. As shown in the preview here, this file contains torque data and speed data in RPM. We can explore this data by using the plot command. So let's say plot RPM underscore data, comma torque underscore data. We can see on the x-axis here is the speed in RPM, and on the y-axis we have the torque in pound-foot. Let's set the speed and torque parameters of our block to these values. To do this, let's go back to our model here, double-click on the engine block, and let's say speed vector is RPM underscore data, and this is an RPM, which is good, and this is torque underscore data, and this is in pound-foot. So let's change this unit here. Next, let's specify the dynamics for this block. To do this, access the Dynamics tab. Let's specify an inertia and an initial velocity for this block. The inertia for our example is going to be 0.1. Let's specify an initial velocity here, which is higher than the lowest speed for our engine. Let's go back to our figure here. Recall that the lowest speed is at 4000 RPM. So let's go ahead and give an initial speed which is higher than this. In this case, we can say 5000 RPM. For more detailed engine modeling, other options in this block include response time lag, data-based fuel consumption computation, and specifying a speed controller to prevent stalling and enabling cruise control and so on. Let's select OK to save changes for this block and go back to our model. Recall that we used 500 RPM for our angular velocity driven direct drive simulation. Our engine, as the data says, operates between 4,000 and 10,000 RPM. We need to reduce the speed supplied by this engine and multiply the torque. To do this, we need a torque converter. Sim driveline provides a torque converter block. To see this, let's go to the Simulink library browser, and under couplings and drives, we can see the torque converter block here. This is a detailed model. However, for our example, let's use a simple gear block and use a high gear ratio to get the necessary torque. To do this, let's go to the gears library and drag in a simple gear block into our model. For our vehicle and engine parameters, a value of 12 has been experimentally chosen for the teeth ratio here. Let's also make sure that this is in the same direction as the input shaft and select OK to save changes. Let's go ahead and delete this connection between the engine and the gear subsystem and put in our simple gear block in between these two blocks here. Now, this simple gear block will enable us to bring the speed and torque within the range for our model. Let's go ahead and simulate this model here. And take a look at the vehicle speed here. We see that the vehicle accelerates and goes through the gear progressions at 10 and 20 seconds respectively. However, after 20 seconds, the speed starts going down towards another equilibrium value. This means that we are not applying enough throttle at this point. Let's give a higher throttle value in our model. So let's go to this constant block and say 0.4 and simulate the model again. We see that there is an error. This error says the engine speed has exceeded the last value of the speed vector parameter. This means the engine speed has gone beyond the specified range. Let's go back to our model here. In reality, we will have the throttle input from a drive cycle data or a closed loop throttle controller. We will cover both of these scenarios in the next video on vehicle drive and control. For the current example, let's specify some sort of a step input for throttle that is lower first for lower gears and then increases when the higher gear is reached. To do this, let's drag in a step block from the Simulink library. So go to the library browser, scroll up, and under Simulink and Sources, find the step block and drag it into your model. Let's go ahead and delete this constant block here. Double-click the step block to configure it. And let's say at 20 seconds, increase from an initial value of 0.15 to a final value of 0.4. Select OK to save changes and connect this block to our throttle input here. Let's go ahead and simulate the model. And take a look at our scopes here again. Now we see that the speed doesn't go down and is maintained better after 20 seconds. We can also see that the brakes are applied at 50 and 75 seconds respectively, although the effects of this on the vehicle speed are very minute. Let's increase the brake force by 5 times here. So let's double click on this block and set this to 500 and set the front brake to 1000 Newton. Go ahead and simulate the model again. And let's take a look at the scope here. Now we see the effect of brakes on the vehicle speed. This effect can also be seen in the torque plot. So let's go ahead and access the torque plot here. We see here the effect of gear changes and the brakes at 50 and 75 seconds. With the engine as the input, it will also be interesting to see how the wheel quantities change. To access this, let's go to the subsystem here, go inside the vehicle subsystem and access the wheel quantities here. We see that the normal force changes whenever the vehicle is accelerating and during gear shifts and braking. We also see that the tires start slipping once the front brakes are applied at 75 seconds. Let's go back to the presentation and do a recap. We saw how to add an engine model to our system. Then we analyzed the results using the vehicle speed and torque to observe the effects of gear shifts and brakes on the system. We also talked about how this affected wheel quantities. In summary, we talked about actuating models with ideal power sources for direct drive mechanism, building driveline mechanisms using gears and clutches, creating multi-speed transmissions and providing gear inputs to the system, and finally modeling engines based on data. This concludes this video.